starting a new lesson today. Excited?
Yes.
All right, so today's lesson is solving systems of linear equations. Oops. I had trouble creating a PDF, so I'm going to post right after the class because my PowerPoint is misbehaving. And actually, it looks like linear algebra can occasionally deal with life questions. So here is a simple problem that translates to a linear system. I'm going to let everybody. So linear algebra can help sometimes. It helps to understand that real life is half happy and half sad. Now you have proof, all right? So now we will actually, starting today, we're going to scale this kind of, so solving a problem like this, we'll scale it a little up. And we'll, 2 days, so this is a system of two equations with two unknowns. In today's real problem, you're often solving linear systems of million unknowns. So you have million equations. So just to show you where we are on our in our course topics, so basically we have finished root finding last time, and today we are starting systems of linear equations. If you would like to refer to your textbook, it's please read chapter 8. Okay? So systems of linear equations formally will name unknowns, and we will typically refer to unknowns as x1, x2, all the way to xn. You have mostly probably solved systems that have unknowns x and y, and maybe x and y and z. That works, or sort of alphabetical order works if you have only up to 3. But if you actually want to expand this to any number of unknowns, I have to start ordering them and enumerating them in order. And this, you can also see how this can help me store this problem in a programming language and basically attack it that way. So we will actually both go to solving of linear systems by hand, just in very small cases, but it's mostly going to be there so that we can actually verify our solutions that we program for larger systems. So typically I will store coefficients as a matrix, A11, A12, all the way to A1n. Those are my coefficients from first equation. Okay? Then A21, A22, all the way to A2n. Those are my coefficients from the second equation, and that's a second row in matrix A, and all the way to nth. And all of the, what we refer to as right-hand side of the equation, those are the equations, those are the coefficients B1, B2 through Bn. They are a vector B. So I can actually, if you take a closer look, you can actually see that this is a multiplication of matrix A and vector x1, x2 through xn, which I'm denoting as x. Okay? So this is a translation of this linear systems into its linear algebra form, and this is also why we did review of linear algebra at the very beginning. Now, so in this particular, what would be my coefficients, or what would be my matrix A?
Negative.
Yes. So 1, 1, 1, minus 1, and happy and sad, whatever numerical value you assign to those. I guess happy would be some positive value, and sad would be equal but negative value. Okay? So life averages to a 0 overall. Okay. So however you want to. So those would be my coefficients. Now, fun aside, this is our engineering motivation. So this is actually taken from one of the master's theses here at the department, but basically you will often solve for stress around the wellbore. How many of you have taken geomechanics? Not at all. All right. Well, you will get to it, okay? You will get to it. The fact of life is that as you go down in subsurface, there is weight on top of you, just simply the rock on top of you, and there's also push and pull from the sides. We refer to those as major stresses, or principal stresses that are acting on you from all sides, and they're often uneven. And that's causing all kinds of fun, basically, as they're drilling. It can collapse your wellbore. It can also create either, typically, if this, so here, this smaller push from the sides is this sigma h with smaller h, and maximal push from the side is this other sigma h. They're typically, they're orthogonal. Not typically, they're orthogonal. So maximum and minimum stress in a horizontal plane, this is a cross-section of a half of a wellbore, are uneven and they're orthogonal to each other, and typically what will happen is that, especially if this difference between the two, the larger it is, there is more chance of crushing rock here at the azimuth of the minimal stress and splitting the rock, which is also fracturing or hydraulic fracturing, here at the azimuth of maximum stress. And this splitting rock is essentially tension. You are in solids, right? Statics. And this is compression. So the maximum compression occurs here. The sort of the maximum tension occurs here. And this is also that if we have pressure in the wellbore that is large, the larger it is, more you're helping this hydraulic fracturing happen. Okay? So it's obviously important for us, A, not to collapse your well, or if you're stimulating, to control what is the size of this fracture, okay? So that it doesn't steal way too many fluids, because if it does, you're going to have lost circulation and you will lose the pressure in your wellbore. So essentially, you have to be in control, and in order to be in control, it is good to know what the stresses are. Long story short, solving for these stresses around the wellbore really comes down to solving a linear system. Okay. So details of it are part of the geomechanics class, but basically there are equations that you go and solve, and those equations come down to basically stating stresses as parameters on all of these grids. You can see the grid here, and basically solving for them using linear system of equations. Now these systems are much larger than 2 by 2, okay? So there will be as many elements as you see here. Okay? Of course, if you want to solve in 3D, they will be even larger. So it's important to be able to effectively solve large systems of equations. This is one example, but basically majority of engineering problems that we solve today are linearized and ultimately come down to solving some system of equations over the other. Even when systems in many problems are nonlinear, systems might be nonlinear. In order to solve them, you linearize them on the way, okay? Because those are the fastest problems. So basically, at the crux of the engineering is knowing how to effectively solve large systems of equations. All right. So just a general definition, okay? If I have Ax equal to B, in order to uniquely solve for these unknowns, I should have as many equations as I have unknowns, and those equations also have to be independent. So one simple example is that, oh, if my equation is x plus 1, y is equal to 1, and then I just multiply it by 2. 2x plus 2y is equal to 2. I didn't bring anything to the table. It's not going to help me to uniquely solve the problem for x and y. Okay? So I still have really one equation. So those equations should be independent. The name of it for it is independent. Okay? So if I have more equations than I have unknowns, that's kind of rare, but that's called overdetermined system. So then some of these equations that are extra be better a proper multiple of some other equation. Okay? Or more often, I will actually have less equations than I have unknowns. So my system is not completely determined. That's not necessarily bad. In the sense that I often want to have some room to move when I'm solving a problem. Let me give you one example. Let's say that I'm solving a problem of traffic in Austin. Okay? So problem of traffic in Austin comes down to how many cars per minute do I have through each street and intersection, right? And I want things to run smoothly. And technically, if I imagine a system that I put together, and actually you can put together, it's a mass conservation problem really, because whatever comes into an intersection better leave that intersection unless you had a car crash, okay? So basically, if I set up such a system of equations, and we've actually built one of the examples here, then do I really want to have a system of streets where only one solution is possible? And unless I have precisely 3 cars per minute on Congress Avenue, I cannot solve the traffic problem in Austin? That'd be kind of too restrictive, right? So typically we actually, underdetermined problems are actually welcome because they leave you room, okay, to actually have multiple solutions that work for a specific problem, okay? So don't be scared just because you see underdetermined problem. It's actually kind of a good thing because you have room to move around. All right, so those are some definitions. And then there are some special matrices that we will mention in the process. So one is a diagonal matrix. That is a very simple system where I have coefficients only along the diagonal. So if I go back to a system of equations here, that means that I would have only a11 x1 is equal to b1, a22 x2 is equal to b2, all the way to ann xn is equal to bn. So that's extremely easy to solve. It's called decoupled. Okay? So from first one I get x1, from second one I get x2, and all the way down to the last one where I get xn, I can very easily solve a diagonal system. Those are too easy, and they don't happen all that often. Technically, formally from linear algebra, I know that my inverse of my matrix is a matrix such that when I multiply my matrix A by this inverse, I get identity matrix, okay? Or the other way around. So in this case, I will typically look at square matrices, okay? And so I can either multiply square matrices, I can multiply in any order, okay? And either way I multiply them, I will get an identity matrix, okay? And formally, if I have an inverse of a matrix, okay, then basically, if I multiply my system AX is equal to B with this inverse, I'm going to get that identity times X is equal to A inverse B. So formally, my X is actually A inverse B. Okay. And technically, you could say, well, okay, so our solution to the system of equations is done. All I need to do is I multiply A inverse to my B, and I'm done. Except that I rarely know what A inverse is. And effectively, finding inverse of any matrix that I give you comes down to solving a system of linear equations. So essentially, it's not necessarily inverse of a matrix is not something I have a formula for unless I'm in a 2D or a 3D system. Okay? So for smaller cases, yes, we do, but for anything larger of interest, I don't have a formula for inverse of the matrix, so I still have to come up with numerical methods to actually solve either the system or for this inverse. And finally, we will also look at symmetric matrices, or just mention them all the way. Those are the ones where basically when I look at across the diagonal, I see the same elements. So if I transpose this matrix, I get the same matrix. Okay, so before we actually go to some further cases of special matrices, I'm actually going to give you a worksheet, so we will actually work through some simple problems to get some idea. Everybody was like, we are over to watch out. negotiation going on? Why not Friday?
What?
You have a test on Friday? How many of you have a test on Friday? Oh, two people. So, I would like you to go, and I'm actually going to turn this off. So I would like you to work through some of these problems, just to think through, okay, what can we expect from systems of equations before we actually start defining the ways to go through them. So in the first problem, I would like you to simply remind yourself how to solve a 2 by 2, whatever method you please. That was good. And then in number 2, I want you to visualize this solution. x1 being x, x2 being y, so plot the solution. So you need to x1 versus x2 versus x1. Here you will draw. So in number 2, you will assume x1 and x2. Yeah.
X1 is 2 and x2. Are they just like
So how do I plot the line?
x1 is actually
Plot
x2 is
a
y.
line exactly. What do I need to plot a line? Points. Find 2 points that are lying on the first equation is a line. Second equation is a line. Precisely. So they intersect at the solution, right? Oh, yeah. Wait, what?
No, but x2 is y.
This is precisely what I'm doing. If I'm just thinking, you're just looking. You're tired, you're like, yeah, whatever she said. This kind of forces you to think.
X is 2, then it's like your vertical, right? So we're taking x2 and x2 is y. So we're taking x2. So x2 is, because if x2 is y, with that,
If you really want to, you can flip it. It's just a matter of perspective. This is the section of 2.
so we're supposed to intersect it.
At up. Single.
Well, everything dollars. I think there's something you're missing.
So key insight is that each of the equations is actually representing a line in this 2-dimensional x1, x2 plane, right? So I can pick 2 points on that line of any choice, pick 2 values of x1, find the appropriate x2, and those 2 points will define a line.
line planes.
And I have a slightly different system here, but the idea is the same. This is a slightly different system, but again, if I plug in two values of x1, I can get x2 and I can plot a line, and I can plot another line, right? So your two lines should intersect at, no, this is just a slightly different system.
It's supposed to be too long, like.
Yeah, your line.
Well, because like I thought it was so that enough wasn't I think it's line for trying to see. I think it'd be intersection.
I'm saying, I think it's wide.
Oh. I don't have a scan of the.
So these are your sections for a line.
So the solution that you plot is a point that is at the intersection of two lines, right? And you should get the same point where you intersect these two lines as the one that you computed. Now, what would happen if I had three unknowns? So I was in three dimensions, x1, x2, x3. And I had a linear equation. 3x1 plus x2 plus x3 is equal to 7. So what is that an equation of? Plane. So how many planes do I need to define a unique point? Intersection of three planes, right? So I would have to have three equations if I had three unknowns to uniquely solve the system. If I had only two, my solution to the system is a line, okay? So I have two linearly dependent, at least two linearly dependent equations. All right, so graphically, okay, now it's extremely hard for us to imagine n-dimensional system. We can imagine three-dimensional. If I add time, I can imagine four-dimensional. But plotting in anything other than 3D or 4D is difficult. But technically, if you have a single linear equation in n-dimensional space, it's still a definition of an n-plane or hyperplane. Okay? Still a plane, okay? And you need n of them to have a unique solution, which is a single point. Right? So it does generalize. Now, do every possible two lines that I can imagine intersect at a point.
Only if they're not parallel.
Only if they're not parallel. Okay? So there are situations where I might not have a solution, okay? Because effectively my equations are parallel. Okay? So I might have simply two parallel worlds and they don't talk to each other, so I don't have a solution. Okay? So basically, go answer number 3.
Would for number for 2C, would it be a plane or not plane, sorry?
A line in 3D. No. For 3 equations and 3 unknowns, it would still be a point already, which is at the intersection of 3 planes.
Okay.
But if I had only 2 planes, then it's a line,
It'd be a line.
and that's an underdetermined system. So number 3, if you had 3x1 plus x2 is equals to 7, and minus 3x1 minus x2 is equal to minus 7. Do you have a single solution x1, x2? No, they're essentially the same equation. Okay? But you do have a solution that is that line. Okay? Now the second one, if your 3x1 plus x2 is equal to 7, and 3x1 plus x2 is equal to 5, what now?
They're parallel.
So there's no solution, right? And there's no x1 and x2 that can satisfy both at the same time. Okay? So it's quite possible that there are systems with no solution. And often engineers are in charge of modeling those systems or coming up with the equations that actually define solutions. And you either have a software package or a applied math friend that helps you solve. Okay? Sometimes you will program the solution as well, but intricacies of numerical methods are sort of the main of applied mathematics. So if you go and model a system and come up with something that doesn't have a solution, you gotta go back to the drawing board, okay? So you're more often than not in charge of actually coming up with the solution. Alright. Now flip the page over and continue with number 4.
Wait, for 3A, there is a solution? Or
There is, and it's that line.
The solution is just, okay.
It's entire line, so I have infinitely many solutions, and they're all on that line. So for any x1 that I plug in, I will find x2. That's all.
And then for the second, for B, it's their parallel.
So there's no solution. And then if you sketch things, okay? So basically 2 parallel lines would be the system with no solution, right? And the other 2 just collapse onto one line. So if you have MATLAB open, you can just, for kicks, plug things in. So for the system that we had on the first page, which color should I go? Give me a color. Purple. Do we have purple? Sure. No, bad choice. Another one.
I will purple tonight.
Yeah, go again. Great. All right. Do we have any gray shirts up there? First gray shirt. I'm going to interpret this as gray. All right. So what is A for this system on the first page? Okay, so 3, 1, minus 3, 2. Okay, so So this is my A, and what is my B? 7 and -4. So basically, if I form X as unknowns, x1 and x2, my vector X, then AX is equal to B is equivalent way to represent that system. And in MATLAB, actually, the numerical solution is obtained by simply dividing formally A divide B. So this is really saying find the solution of the problem AX is equal to B. Okay? And the solution is 2, 1. Is that the same as what you got by hand? Also? Okay. So this is how you will double check your work. Okay. We will both solve things by hand and we will program ourselves solving this system. Here you actually don't know which out of many methods we will actually mention in this lecture. We don't know which one has MATLAB chosen to actually attack this problem. Okay? But we will actually get the inside view of how these methods look like. Yes?
What is a slash diagonal?
So that really, this is just an operator. Okay? It's really saying find the solution of the problem AX is equal to B.
Okay.
And yes, you have to have matching dimensions or else. Okay? So if I throw in A that is different, or let's say that B is, oh, I don't know, 1s of 3, 3. Okay? So if I try to do this, it's gonna yell at me. Because I can't have a 3 by 3 matrix of coefficients and 2 by 1 matrix on the right hand side. I don't have an X so that I can have AX is equal to B, so it's going to tell me matrix dimensions must agree. So this backslash operator in programming, it's called overloading. Okay? So it's an operator that can do different things, and one of its functions is that it can actually solve linear problems. This is really the case, or this backslash operator is really very specific to MATLAB. Everywhere else, you will actually have to type in something so numerical that will give it A and B and return X. So, just to remind ourselves how to do things by hand, go ahead and solve number 6. Okay? Yeah, it's these are simple. Oh my God. Really, Dr. Kodanich? It is 2:30 in the afternoon on a Wednesday. Our brains don't function anymore. So first, you will have to translate it to a linear system of equations, right? It's all linear systems. So x1 equals 2. So first one is really easy.
It's like multiplying this by
So gotta multiply to get my linear system. I have to multiply with x. So multiply. Just because you're done with exam 1, that doesn't mean that we have to forget how to multiply matrices. It's really solving A and B. Right inside. But it's formally like this. if I had 3x equals 5, actually this should not be by 8. Somebody programmed it this way.
Actually, interesting.
Have you finished, B?
Interest rate. These classes are you actually read where you
This should be a test
Where are my
grade
gray shirts?
right here.
Huh?
Test grade.
Oh yeah? 30% of that. 30%. Who's great? Somebody about it. So what are the solutions here? X1 is -1. X2 is 2. And X3. So essentially, this second equation here, first equation is simply x1 is equal to -1, so I had it directly. Second one, when I multiply with x1, x2, x3, I'm going to get 3x2 is equal to 6, right? So x2 is 2. And third one is 5x3 is equal to -15, so x3 is equal to -3. Simple. How about the second one? Where is my... I have more gray. Gray is popular today. And gray shirts are typically not paying attention to me. A, B, over there. So, and I think I forgot one up there. All right. So, did you solve this problem B? So basically, this is a so-called triangular system, okay? This is upper triangular system because only upper triangle of my matrix A is full of numbers and the rest are 0. Okay. So when it translates to equations, this is -2x1 plus x2 plus x3 is equal to 9, right? And then 3x2 minus 2x3 is equal to -1. And finally 4x3 is equal to 8. So my x3 is 2, because I start from the bottom one. Then I have x3, and I can plug it into the other 2. Okay? So when I plug 2 into the second equation, I will have 3x2 minus 4 is equal to -1. So 3x2 is 3, right? And I will find x2 to be 1. And now that I have both x3 and x2, I can plug it into this equation. Okay? Then -2x1 plus 1 plus 4 is equal to 9, right? So -2x1 is equal to 4, and x1 is going to be -2. Yeah? Did I do that right? Doing it right. Now, how will I check myself? Well, let's check myself. Okay, so A divided by B. Whoops. Oops, I'm plugged in uppercase B. That's fine. It's -2, 1, 2. I had a typo. I plugged in uppercase. Okay. Now trust me, programming this, what I just did, is called backward substitution. I can see elements of an algorithm here. Okay. I start from the bottom, where its solution is simple, and then I plug things in as I go in a nice little for loop. Okay? And within that for loop, I sum up what I already know in another for loop and subtract it from the other side, and then find the solution. Is everybody following my thread of thought? Okay? So actually here, when I was in the upper row, I times x3, and if I had n of them, I would be able to do a nice for loop with n minus 1 of them. Okay? So I would sum up. We know how to do sum in a for loop. I would subtract that sum from 9, and then my x1 is whatever I subtracted divided by coefficient a11. Is everybody following my? I lost you completely. Huh? You're gonna get it formally. I'm just kind of trying to hint that there is an algorithm here that I could actually let computer do. What if I had 1,000 by 1,000 here? I don't want to do that by hand. Okay? Nice little for loop goes a long way. Yes.
Is there a situation with MATLAB the backslash operator won't work and we'll have to program it ourselves?
Yes, problematic A. Okay, so in those situations you might have issues solving yourself as well, but you're a human, so you would figure it out. So let's actually do my A. I'm gonna formally just put 0, 0, 0 here, which is basically no equation. So if you do this, okay, it's gonna have trouble because essentially I don't have a unique solution. Okay. So if you're A, and we can actually, that's one of the definitions. If your A is so-called a singular matrix, doesn't have an inverse, and matrices that have some of the rows that are multiple of others are such examples, or they're just zeros, those matrices will not produce a unique solution, and that's trouble for the numerical algorithm that assumes that A has an inverse. Okay. So we could, oh, wow, hi. You could actually compute an inverse of A. It was a 0, 0, 4. You can compute inverse of A if you're interested as this. So there is a formula for it. So inverse of A times A should be very close to identity. I have some little numerical issues when multiplying things, so there's a very small number here very close to 0, so this is approximately identity. So inverse of A times A should be identity again. We know why these numerical errors show up. We had a whole lecture on errors. Okay, so there's a very small number sitting here. This is really identity.
And if you use inverse A times B, you get X.
So inverse of A times B, that'll be your solution, yes. Okay. But again, finding an inverse is an algorithm underneath that is similar to solving a system of equations. We're going to get to that. We're going to actually devise an algorithm. Right. So just to briefly go back to my presentation, as a recap, in order to have a solution, and that's also for your numerical algorithms that we will program to work, okay? We need as many unique equations as unknowns. So if I have in 2D 2 parallel lines, there will be no solution. Solution is really one, there's basically no solution at all. Those 2 equations could collapse into one that's called linearly dependent. Okay? They're essentially multiple of each other. Or if I simply add up 2 equations together, that's not new information. Okay? Sometimes you might not have parallel, they're not parallel lines. Mathematically, there is a unique solution. But because they're nearly parallel, numerical algorithms, specifically because rounding up of the numbers and not precise representation of numbers in a computer, you might actually have trouble finding the solution. So algorithms will struggle with systems of linear equations that have some of the equations nearly parallel or nearly linearly dependent, and those are called almost singular matrices. So matrix A has to be non-singular, it has to have an inverse, or in other words, these rows have to be linearly independent. Okay? So one thing that we can always do, we can flip order of equations, it doesn't matter, for solving the system. We can multiply both sides by a number without changing the system. We can add and subtract two equations, we're not adding new information. And if I add up two equations, I can replace one of them with that added equation. That's not changing the solution to my system. Okay? So there are still simple things that we can do in order, and that's actually what you're doing when you're solving by hand. You're just not calling it necessarily that way. Alright, we're gonna continue next time.